At this point, I think it's fair for us to call ourselves experts in how the deflate scheme works, since we've seen the deflate scheme at such a low level that we're now definitely familiar with all of the strange twists and turns, the intricate procedure necessary to encode data in the deflate format. But that doesn't really mean that we're experts in why deflate does what it does, why the design decisions behind deflate were made. Some of the decisions behind deflate clearly were pretty complicated, but the question is whether they were necessary. Is it true that maybe every compression scheme has to contend with issues like the CL code and the CL code length table from deflate? Or is it true that those were only necessary in deflate itself to try and ameliorate some of the issues that showed up earlier in the encoding process? Or maybe they were useless. Maybe some of those weird decisions that we encountered in the deflate lecture actually didn't help anything in the grand scheme of things. We don't really know. We don't really know which of those three categories a decision falls into until we have some point of reference. What we need is a comparator, some other successful compression scheme that we can analyze. We can look at the design decisions behind some other compression scheme to decide which decisions, even if they were sort of unsavory, had to be made for every scheme. Which weird, unpleasant features of a compression scheme are sort of universal, and which decisions were unique to deflate, and maybe also which of the decisions made during the design of deflate turned out not to be necessary after all. So we need some point of reference. We need some comparator. And so I think it's about time that we talked about BZip. But first, speaking of time, I want to talk about wristwatches for a minute. And a full disclosure, I don't wear a wristwatch. And one of the reasons for that is that, it's 2023. But I've never worn a wristwatch, and I just hate the feeling of wearing something on my wrist. It's the same reason I'm not that big of a fan of wearing long sleeves. But I can still have respect for technological milestones, and this watch is definitely a technological milestone. This is the Seiko Astron, which was unveiled in late 1969. And by late 1969, I mean like end of December. So if you wanted to go out and buy this thing, you'd have to wait until, I'd say, mid-1970, probably at the earliest. But in any event, it was eventually made available for sale, and it was the first quartz wristwatch made available commercially. So it's a wristwatch that relied for its timekeeping ability on the resonance of a quartz crystal. So the idea of quartz clocks wasn't new in the late 60s. That had been around for a while by then. And the idea is the resonance of a quartz crystal, once you know which particular type of quartz crystal you're dealing with, once you know its properties, its resonance can be predicted very accurately. And so if you have some way of measuring resonance, so if you know that you have a quartz crystal that'll resonate at 32,000 hertz resonance frequency, so 32,000 times per second, and you have some way of counting, of measuring that resonance, then you can keep time very accurately. And so the innovation behind the Seiko Astron was that it was able to encapsulate this entire quartz clock mechanism, so a battery, a quartz crystal, and a bunch of solid-state electronics, as well as some mechanical parts, because it was an analog watch, so there was the need to still drive the actual moving hands on the face of the watch. It was the first to encapsulate all of this stuff into a package small enough to wear on your wrist. And according to the marketing, the Astron was accurate to within 5 seconds per month, which means if I were to set it this morning and come back in a month, I could expect that it would be off by less than 5 seconds in either direction. I mean, that's 1 minute per year that it's going to go off. I did some research into this. I say it was marketed this way because I couldn't find any independent data to verify that. It appears, based on the other very, very cursory reading that I've done, it appears that this is a reasonable claim to make. It seems like this is very plausible for a quartz watch, especially because although this watch was the first commercial quartz wristwatch, it makes sense they try to make it as accurate as possible to try and be as impressive as possible because it was very expensive. If you go out and buy a cheap quartz watch, so over the last 50 years when quartz watches have become ubiquitous among people that wear watches, I believe, based on reading I've done, that you can expect a typical quartz watch to be accurate to within about 15 seconds per month. So that's basically half a second per day that I expect the watch to go off, which is pretty good. If I want to pay extra, I can find quartz watches that are accurate to within 1 second per month or less. And so in general, quartz watches are pretty accurate. Quartz clocks, because they rely on that quartz crystal, which is so consistent, we can expect it to have really high accuracy. And so the Seiko Astron was later actually honored as an IEEE milestone in electrical engineering for the achievement of bringing a quartz clock to wristwatch size. The reason that I bring it up is I want to talk about this unveiling of this watch in 1969 and this accuracy of the quartz crystal and how that affected people's view of the watch as it was at the time in the late 1960s, and maybe what the watchmakers felt about this. Now, you can go and read up on this. It's actually sort of interesting that the watchmakers at the time would have been, I guess, individual artisans. They were predominantly, or the watchmaking industry was concentrated in certain parts of the world. Even these days, if you think about old-fashioned mechanical style watches like this one here, you might associate them with, for example, Switzerland. So there were lots of watchmakers in Switzerland. And watchmaking was a traditional sort of artisan craft that required a huge amount of training. And creating these mechanical watches relied on innovations produced over centuries. Literally centuries of development went into the mechanisms of mechanical watches as they existed in the late 1960s and as they exist today. And as you can see, so a mechanical watch relies on this mechanical movement typically actuated by a spring. So the spring gets wound up either by the user of the watch or by their movements throughout the day. So as your wrist moves around, that can automatically wind the watch. One way or the other, potential energy is stored in a spring. I don't know where the spring is in this thing, although that looks like that might be a spring, I don't know. And the energy stored in the spring is used both to drive the carefully crafted mechanical components that keep time, so balance wheels and things like that, but also all of the components that drive the hands on the face of the watch. All of these things have to share the mechanical energy stored in the spring. As the spring winds down, the amount of energy in it decreases, and that can affect its ability to keep time. So time-keeping components, this complicated, intricate mechanism, have to be crafted to compensate for the varying amounts of mechanical energy available in the spring, and the fact that they're going to be affected by inertial factors, like if you're wearing this mechanical mechanism on your wrist and you're moving in some direction, or you're moving your wrist or waving your hands in the air, that will have an impact on the motion of the mechanism of the watch. And so, of course, the watch has to be designed to accommodate that. And after centuries of development, centuries of research and development to create these intricate mechanisms that required this traditional artisan craft to create or repair, mechanical watches in the 1960s, and frankly today, are accurate to within maybe a few seconds per day. If you go out and buy an expensive mechanical watch today, you can probably get it among the variety of expensive mechanical watches. Apparently, it's not uncommon to be able to find some that are accurate to within maybe 2 seconds per day. So I set the watch today, I come back tomorrow morning, and it's off by 2 seconds. Okay, well, that's not that bad. That works for the day. But on the other hand, cheap quartz watches, even the ones that are accurate to 15 seconds per month, blow that out of the water. And if you think about it, the fact that the internal mechanism of the quartz watch is so incredibly accurate means that maybe there isn't such a need to spend so much money or spend so much time designing all the other components of the watch. If the quartz crystal is so good at keeping time, maybe you don't necessarily have to worry about whether you buy the absolute most expensive parts for all of the other parts of the mechanism. So for example, whatever mechanism is driving the hands of the watch, things like that. You're relying on such a great internal timekeeping device that you don't necessarily have to ensure that the rest of the watch is absolutely as accurate as possible. You actually have accuracy to spare. Whereas if you're a watchmaker designing a mechanical watch, every single tiny component has to be precision machined and fit together perfectly, because any component having extra friction or anything else could upset the overall accuracy of the watch. And so after centuries of work in crafting these mechanical components and fitting them together perfectly, even then, mechanical watches couldn't really compete in terms of accuracy with quartz watches. It just couldn't happen. And I guess life's not fair sometimes, but even the most intricate mechanism trying its best to preserve accuracy at every level can still be blown out of the water if you just find some fundamental device like a quartz crystal to bury inside the mechanism that's just way more accurate than anything you could come up with. Okay, so why am I talking about this? Well, I'm talking about this because I've made a couple of references in the last few lectures about how I think that deflate, with all of its intricacy, is like the precision mechanism of a mechanical watch. It's all of these pieces fitting together perfectly and intricately to produce the best compression possible. We noticed in the deflate pipeline, one of the reasons it's so complicated and convoluted is that at every single step, the mechanism has to save one bit here and one bit there to try to achieve the best compression possible. So deflate is like a mechanical watch. What we're going to see in this lecture is that this watch is more like BZip. BZip2 has a quartz crystal. It has the BWT. We saw in the last lecture some promising signs that the BWT might be quite helpful for compression. BZip2 relies on the BWT and a bunch of other techniques that complement the BWT, and its internal mechanism is so good that BWT by default just has a natural advantage over Deflate in most cases. In general, one can expect BZip to have better performance than Deflate. And what we'll see that means is that when it comes time to design a compression scheme around the BWT, like BZip2, there isn't as much of a need to save one bit here and one bit there. The quartz crystal is just so good that you've got accuracy to spare. And we'll notice in the BZip bitstream, which we won't cover in the same level of detail as Deflate, but we'll have enough detail to notice that in the BZip bitstream, there are actually even cases where bits are deliberately wasted, just for convenience, to make debugging easier. Bits are thrown away at will, something Deflate would never do. And that's because, really, BZip just has such a good internal mechanism, the equivalent of a quartz crystal, that it has bits to spare and still can get better performance, as we've been seeing over the earlier lectures in this course when we've occasionally looked at benchmarks comparing GZip to BZip. So since the late 1990s, which is when BZip2 came out, I think BZip has enjoyed a pretty comfortable sort of second place. It's the other standard compression tool in the Unix ecosystem. I've referred earlier in the course to the fact that I consider the big three compression tools these days to be GZip, BZip, and LZMA. And I understand that all three of those are 20 years old at least as of 2023. It's certainly true that there are newer lossless compression tools that have come out. And one of the reasons that we're spending so much time on GZip, BZip, and LZMA is that first, modern compression tools have learned a lot from the big three, GZip, BZip, and LZMA, but also because when it comes down to it, if you're going to send me a compressed file, so outside of the context of being a compression expert, if I'm going to receive a compressed file from somebody randomly in 2023, odds are it's been compressed with GZip, BZip, or LZMA. And actually, these days, odds are still very high that GZip has been used. The odds are generally in favor of GZip even now, even though GZip and Deflate are the oldest of the big three. Because if somebody sends me a compressed file these days, it's probably a zip file. And although zip files support other compression formats, odds are they've just compressed it with Deflate. So we owe a lot to Deflate and to BZip, and that's one of the reasons we're going to look at those two in great detail. And so BZip is the second one we're going to look at. I would argue that BZip is an example of a successful scheme design for the same reason I can argue that about Deflate, because both BZip and Deflate have become ubiquitous. They're everywhere. If I sit down at a random machine and look for compression programs, the ones I'm likely to find are Deflate and BZip. And so it's important that we study at least two in great detail, and that's why we're going to study these two. The reason we need to study two is because we don't really truly understand Deflate until we understand, I guess, the competition, and vice versa. We can understand both schemes better by having a point of contrast and being able to look at what is the same between both schemes, what compromises do both schemes apparently have to make versus what things do both schemes do differently really helps to enrich our understanding of which unsavory decisions are just universal. Are there some aspects of designing a compression scheme, like how to store code length tables or something, that are just always a mess? Or are there some aspects of the Deflate scheme that, although they seem to work, turn out to have been overly complicated? So I want to talk mostly about BZip in the vein of having some point of contrast. I am not going to cover the BZip bitstream at a bit-by-bit level. I'll cover it at an overview level, so I'll talk about what goes into the bitstream, but not the exact organization of a BZip block in terms of the bitstream. That is because lectures like the Deflate lecture are a sort of once-per-course thing. I think we're sort of out of patience for another lecture of that scope. So I'll talk about the BZip bitstream at a high level, but I won't go into the bit-by-bit breakdown of how we create blocks. One observation I'll make right off the bat is you'll recall early in the Deflate lecture, a lot was made of the fact that in Deflate, there's a significant bias towards pushing the least significant bit first. If we have our bit stream, so suppose I'm pushing bits into my bit stream, and I end up with 8 bits, so now it's time to push a byte out of the bit stream, recall that in Deflate, the first bit that you've added to the bit stream will become the least significant bit of the eventual resulting byte, and then we go from least to most significant as we go from left to right. The opposite is true for BZip. This actually appears in the BZip documentation. It says, Note, unlike deflate, in BZip, when you have enough bits to form a byte, the first bit becomes the most significant bit of the byte. And that tends to be the case across the scheme. In general, things go most significant bit first, so sort of big endian bias, which is a significant contrast to the big rule number one issue in the deflate lecture. Now, there isn't really an equivalent rule number one for BZip, because there are a few cases where things do get pushed least significant bit first. One of the most noticeable differences we'll see later in this in the BZip lecture, later in this lecture about the BZip bitstream is in fact a place where things get pushed least significant bit first. So there isn't the equivalent of rule number one, but one interesting point, I mean sort of trivia, is that it's interesting to see how deflate and BZip are natural contrasts in more ways than one, even going down to things like bit orderings. So the BZip scheme uses a pipeline design, and I think last time I taught this course, I said something like, oh, there's a very tight separation between the stages of the pipeline. That is, we do one stage, and then we're done, and we do the next stage. And I mean, to be fair, although that's true, that's actually true of deflate as well. So if I take a look at deflate, deflate does use a pipeline in terms of what happens to your original data. So before we deal with the weird block header stuff, really though, the pipeline is just two stages. We do LZSS and then we do prefix coding, and that's it. And certainly, as you saw, in deflate, we do one after the other. We do LZSS and then we do prefix coding. We don't go back and forth. I don't do prefix coding and then go back to LZSS. What I observed though, that weird, scary fact I observed at the end of the deflate lecture is there is a feedback loop between these stages. It's true that decisions you make in the prefix coding stage can have an impact on what the best decisions would have been at the LZSS stage. But generally speaking, BZip encoders don't go back and forth. It is still a forward path through a very simple pipeline. BZip also has a pipeline design. As you can see, the pipeline has more distinct stages. This remark is, I think, a statement of one contrast, which is that although it's certainly true that things that happen in prefix coding can have an impact on the efficiency of things that happened, I don't know, at this stage or at this stage, there is no potential for a feedback loop. And what I mean by feedback loop is a case where a decision you make up here that achieves apparently good compression gets sort of canceled out by a decision you make down here. Meaning that if I knew in advance which decisions I made at stage number 4, I might make different decisions at stages 1, 2, and 3, and vice versa. That's the feedback loop. We saw in deflate that could happen because if I have a particular back reference, so a particular length and distance pair that shows up a lot, then it could turn out that this length distance pair gets encoded very efficiently, and therefore if I have any other back references that are, let's say, 5, 10 or something, I might actually save bits, at least in a theoretical sense, by generating 410 instead, because this back reference becomes so common that maybe it's encoded in a very small number of bits. The reason that that's a feedback loop is that there are two decision points here. One decision is when do I generate back references, so that happens early in the pipeline. A different decision in a certain sense is which prefix codes go with which back references. So which prefix code end up being generated for the length symbols. And depending on the prefix codes that get generated, that could change the optimal decision making that I could have made back when I chose my back references, as I mentioned in the deflate lecture. There is no feedback loop in BZip, but it is still true that which prefix codes get chosen for which symbols could have an impact on whether the decisions made at earlier or whether particular things that happened at earlier stages were efficient or not. But there's no decisions that I'm allowed to make in these early stages. So the compressor doesn't actually have a choice for what to do. It's true that something I do in stage 4 could make something that happened in stage 2 or 3 less efficient, but it turns out in stage 2 or 3, I don't actually get any options. I'm required to do it one way every single time, which is sort of liberating because it means our compressor no longer has to agonize over all the possible decisions. We'll see a running theme in BZip is this very straightforward left to right or top to bottom pipeline where you do basically exactly the same thing at every stage. Every single BZip compressor ever does exactly the same thing in the RLE1 stage and in stage 1 and in stage 2 and in stage 3. The only real leeway, the only real flexibility is provided in stage 4, and as we'll see, I have a relatively negative opinion of how useful that flexibility even is. So one notable feature about BZip that I've alluded to already in the last lecture is that the quartz crystal, the thing that makes BZip so powerful, is this pair of transformations, the BWT followed by the Move-to-Front transform. And we've already seen the Move-to-Front transform. If you've forgotten about it, it was a while ago. It was tacked on to the end of Lecture 5. Maybe go back and take a look if you've forgotten. But these two transforms together, of course, don't actually do any compression. They're just size-neutral transformations. Although, as we know, the BWT actually adds extra data because it adds on that BWT index. So the two signature features of BZip actually don't produce compression at all. All of the compression is achieved via relatively fundamental techniques. So certainly RLE is a basic technique. Now, there are two different variants of RLE that get used in BZip, as I've mentioned in previous lectures, but they're both fundamental things. RLE is a very basic technique. And then prefix coding is also, I would argue, a fundamental technique. So generating prefix codes using Huffman coding, that's something you're going to see in pretty much some form of entropy coding, whether it be prefix coding or the alternative, is pretty much going to show up in every lossless compression scheme you encounter, probably as the last stage of the pipeline. So we use, and prefix coding, of course, is also used by Deflate. So the two schemes are sort of even on that front. So the big advantage is apparently achieved here. It's apparently achieved just in these two RLE stages. It's the fact that RLE is so good at working with the output of stages 1 and 2 that gives BZip its advantage. It actually turns out that RLE 1, as we'll see shortly, doesn't really give us the advantage. Mostly it's coming out of the stage called RLE 2. So anyway, I mentioned in the last lecture that the BWT output, and maybe you saw that from the examples, the output of a BWT is pretty amenable to things like RLE and Move-to-Front. So one of the reasons is that the BWT tends to produce, ideally, if all goes well, we can expect the BWT to contain long runs of consecutive characters. And of course, RLE can do a good job with that, but so can the Move-to-Front transform, because the Move-to-Front transform, as you may recall, transforms sequences of contiguous sequences of consecutive characters into runs of zeros. And so it turns out that that sort of amplifies the effect that the RLE2 stage can have. And we'll see that later in this lecture. So anyway, I'm just going to go through the pipeline from start to finish. So the first stage is one of the two RLE stages, because there are two of them. I'm going to call this one RLE1. And the RLE1 stage is the BZip style RLE that we've already seen in this course. So recall that the BZip style RLE scheme that I've mentioned earlier, so in lecture number 5, for example, is a scheme where we perform run length encoding, but we only store a run length once we've already seen a run of length 4. So we don't store run lengths if we only see one character by itself or two characters in a row. Only when I've seen 4 of the same character do I bother encoding a run length. And that's one way of splitting the difference, of making a compromise that doesn't waste a lot of space encoding run lengths that aren't going to help us, because we know that encoding runs of length 1 or length 2 can often be sort of difficult. It can often result in expansion. So here I've got a sequence with, this has 4 S's in a row. Later I've got a whole bunch of R's in a row. Then I've got, I think this is 5 A's in a row, and then later I've got 2 A's in a row. So we'll take a look at the runs. Here's my run of R's. So apparently it's a run of 12 R's. I've got the first 4 here, and then after the first 4, I must encode a run length. And so I encode how many more R's are there. There could be 0. In this case, there are 8. So I've got 12 in total. And then later, I've got a run of 5 A's. So my 5 A's, I've got 1, 2, 3, 4 A's. And then I say there's one more A. Okay? And earlier on, I had a run of 4 S's. So I've got S, 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 S. And there are 0 more. So I have to encode the run length as just the value 0. I have to encode that there are 0 extra. And we can see in this case, if I'd stored the run as just 4 S's, it would have required less space than if I stored it with this run length. So as usual, there is going to be a case where we get expansion. Notice that if you think back to the reasoning we were doing in the lecture on RLE, lecture number 5, about this doesn't otherwise achieve very much efficiency. So certainly the BZip style scheme, only encoding runs of length 4 or greater, doesn't artificially inflate short runs, like runs of length 1 or 2. But we're actually storing run lengths as full 8-bit values, even though, of course, in this example, the runs are not nearly long enough to warrant an 8-bit value. And so what I get out of my RLE1 scheme, when I'm done performing RLE1, is a sequence of 8-bit symbols. I get a sequence of 8-bit symbols going in. I get a sequence of 8-bit symbols going out. And that's because I'm representing the run lengths with 8 bits. So once I'm done with this, if I hand this over to the next stage doesn't really care what each symbol is meant to represent. The next stage gets a bunch of 8-bit 8-bit stuff. It gets a bunch of bytes. So as far as the next stage is concerned, this value here could be a run length. It could just be a representation of the byte 0, the literal character 0. That's really none of its business. When I decode the RLE1 stuff later in the decompressor, of course, I'll have to care about that. But I'll know, because if I've just seen 4 characters in a row, I know that the next 8-bit sequence is a run length. If not, the next 8-bit sequence is just a literal value. So I can encode runs of length up to 255, and of course this does give us expansion in some cases, and the run length, and the way I've encoded run lengths isn't necessarily the most efficient in a general sense, but remember that when we use RLE inside of a pipeline, sometimes using up a bit too much space isn't a big deal, because the next stage of the pipeline could help me with that. There actually are reasons why keeping everything in a consistent form, even if it's a bit space inefficient, can be helpful, because it makes it easier for the next stage to go to work. And so, of course, in the worst case, this could end up expanding the data by 25%, because I could have just a bunch of runs of length 4. And every run of length 4, I take a loss. If I have runs of length 1 to 3, I break even, because a run of length 1 just gets encoded as 1 byte, so it stays the same in size. If I have a run of length 5, I also break even. And if I have a run of length 6 or greater, I make a profit. I actually achieve compression. But if I have a run of length 4, then I see an expansion of 25%. So I add 1 extra byte for every 4 bytes. We could also, as a fun exercise before the exam, maybe think about determining the maximum compression ratio you could possibly achieve on any input in this single stage. Performing that kind of analysis on RLE1 or any arbitrary scheme that I make up on the exam, that's a valid exam question. What's interesting about the RLE1 stage is, I like having BZip as an example of a long pipeline. There's a lot of different stages. What's weird about BZip, though, is that it appears in hindsight that RLE1 didn't really help the pipeline achieve compression. And commentary from the designer of BZip, a person named Julian Seward, suggests that actually RLE1 wasn't added to the pipeline because of its compression benefits. It was added for a completely different reason, which is sort of sketchy in hindsight. Like in terms of design decisions, I don't know if it was a good one. But on the other hand, BZip is a well-designed scheme. As a software designer, it's easy for people to be a backseat driver and say, oh, that was a bad decision in hindsight. But hindsight's always 20/20. When you're actually preparing a design, you occasionally make decisions that don't age well. So it turns out, so the designer of BZip it concurs on that maybe this was a bad design decision, so I'm not speaking too far out of turn here, although I'm entitled to my opinion. Seward actually calls the RLE1 stage sort of a mistake, although maybe it's sort of a harmless mistake, like it doesn't make the compression worse in general. Seward acknowledges it was only added to mitigate an algorithm performance issue that had to do with the way the BWT was implemented, and it turns out the BWT could have just been implemented differently. This belongs more in the previous lecture. I talked about that briefly in the last lecture. I'll just give an overview. So, as I mentioned in the previous lecture, one thing we're not going to cover in detail is the fact that BWTs can be computed using something called a suffix array, which is related to a data structure called a suffix tree, neither of which we are going to cover because we don't have infinite time in this course. And because your assignment 2 is not to implement BZip, so you're not going to implement a BWT probably. If you do on assignment 4, then maybe implementing a suffix array or suffix tree could get you some extra marks, whatever. So you can implement BWTs with a suffix array. To construct a suffix array, there are a variety of ways of doing this. One relatively straightforward way involves generating all the suffixes of a particular string, of your input string, and then sorting them. So if we look at all the suffixes of this input string, it's this collection here. So one of the suffixes is the suffix that eliminates 0 characters from the beginning, so it's just the entire string. And so we generate all the suffixes and then sort them. If I have an input string with a long run of contiguous characters, then when I generate all the suffixes in order, some of them will be already in sorted order. All of the ones that are part of this long run of A's are guaranteed to already be in sorted order, either in forward sorted order or in reverse sorted order, depending on what order you generate the suffixes and what character appears over and over again. For the sake of this example, I've used the character A, and you can observe if I do a lexicographical comparison of strings among this block, block, they are all already in sorted order. That is to say, AASP will come before ASP in the dictionary. So they're already sorted. And you can imagine, although this example is the largest one I can fit on a slide in this notation, if this were a run of 1,000 A's, you'd have a very long block of of suffixes that are all in sorted order. And I could take this further. What if I had a string that was literally just a huge run of A's? Well, then every suffix would would already be in sorted order, and even worse, to actually perform the string comparisons, if you think back to the last lecture, when I want to sort this collection of suffixes, I have to compare pairs of strings in my sorting algorithm. Well, if I want to compare these two strings, it turns out that this string here would probably be considered lexicographically less than the string above it, because usually shorter comes before longer when all else is equal. The thing is, to reach that conclusion, to figure out that these two strings are, they match but are not the same length, so they're matching up to the fact that one string is one character longer, I'd have to actually look at I have to compare the first character of the two strings, and the second character, then the third character. I have to loop over a huge amount of the string. And so performing these string comparisons is something that we maybe can't get around, that RLE1 might help with. But it turns out the reason RLE1 was added was because when you have these huge blocks, which could occur in some inputs because of sequences of consecutive characters, when you have these huge blocks that are already sorted, and you choose a sorting algorithm that performs badly when the input is already sorted, then you're going to have a problem. So your sorting algorithm will take too long. Now, those of you, which is all of you, that have taken an algorithms course know that if you're choosing a sorting algorithm that performs badly on inputs which are already sorted, and you expect that your input might be already sorted, maybe you've just chosen a bad sorting algorithm. That's the remedy. Choose a different sorting algorithm. That isn't what happened in the case of BZip. So in the original paper about the BWT by Burrows and Wheeler, that paper proposed using a certain variant of quicksort to sort suffixes. And you'll recall from your algorithms course that quicksort's worst case performance, if you're using deterministic quicksort, shows up when you have inputs that are already sorted. So if I give quicksort typically an array that is, so if it depends on how I'm choosing the pivot for quicksort, but if it's any deterministic pivot selection rule, you can end up in this situation. If I run quicksort on an array that's already sorted, then quicksort will often descend into n-squared behavior, which is not great if the array is, reasonably large in size. And so because the original BWT paper proposed quicksort, I guess that meant that quicksort got propagated through as the sorting algorithm of choice in implementations, including the one used in BZip. And so we had this problem of, if there are a bunch of suffixes in a row that are all sorted, then quicksort's going to perform badly. We better modify our compression scheme so that that doesn't happen. Now, okay, Seward acknowledges this might have been an unnecessary optimization. I would consider this pretty much a textbook example of premature optimization. You're worried about something being slow, and so you sort of make arbitrary choices to defend against it, as opposed to analyzing it, taking a step back, and thinking, hey, maybe the problem isn't the input, the problem is quicksort. Why not just use a different sorting algorithm? But anyway, RLE1 was introduced to break up those runs of consecutive characters, to mean that, I guess, to result in there being shorter sequences, shorter blocks of suffixes that are already in sorted order, and preventing quicksort from having a real meltdown, from degenerating into n-squared behavior. So there are a couple of things. The reason I have a problem with this is that, well, why not just not use quicksort? So that's one thing. If you use merge sort, you wouldn't have to worry about the temperamental behavior of quicksort. But actually, as it turns out, since BZip2 came out, new suffix tree construction algorithms that rely on inherent structure in the suffixes. So that it turns out you don't actually need a general sorting algorithm to sort this, because there are certain structural similarities between suffixes that you can take advantage of. There are actually now construction algorithms that are linear. So if the designer of BZip hadn't, jumped the gun there and added the RLE1 stage to defend against quicksort, not assuming that quicksort is the only possible option, the RLE1 stage wouldn't have been necessary at all these days, because we could have been using this faster construction algorithm that doesn't require RLE1 first. What's even more odd is that it appears that the original BWT paper, which set in motion the sequence of events that resulted in quicksort being chosen, the original BWT paper actually also proposes a modification to quicksort that fixes the problem. So it's all sort of weird. I should add, I guess I have to declare my bias. For full disclosure, as many of you know, I rather don't like quicksort. I'm a big fan of merge sort, but I'm not a big fan of quicksort. So if what you just heard sounded a lot like some guy grumbling about quicksort being dumb because he doesn't like quicksort, maybe that's what it was. Whatever, I think I made a few valid objective points. So anyway, we're stuck with RLE1. I think it can help and achieve compression in some cases, and it doesn't generally create unnecessary expansion. And one way or the other, BZip is still pretty good, so RLE1 I think is harmless. So whatever, RLE1 is there. We have to perform it. We have no choices. The compressor doesn't have a choice for which runs to encode. It must encode every run of length 4 or longer by adding a run length as an 8-bit value. So after the RLE1 stage is over, the data is split into blocks, because as we know, the BWT works on a block basis. We have to split the data into blocks to run the BWT. So the size of the block is dictated by the quality setting provided on the command line. So as you know, if you want the best compression possible with BZip or with GZip, you would use the -9 flag on the command line. If you want higher speed but maybe lower compression, you would use the -1 flag. So if I use BZip-1, I'm getting 100 kilobyte blocks when I run the BWT. When I use BZip-9, I'm getting 900 kilobyte blocks. And we know from the previous lecture, or we have at least an instinct from the previous lecture, that the larger the blocks are, the more likely the BWT will produce really good results, because the more data the BWT has access to, the more likely it can create those patterns that we're looking for. But on the other hand, the larger the blocks are, the more complicated it is, the more difficult it is to actually compute the BWT. So BZip-1 uses 100 kilobyte blocks, BZip-2 uses 200 kilobyte blocks, and BZip-9 uses 900 kilobyte blocks, and that's the largest you can make a block. Now, by contrast, if you use GZip-1 or GZip-9, those are also meant to connote quality versus speed, and so GZip-1 is faster but results in worse compression. GZip-9 results in better compression. However, the set of settings that are modified between -1, -2, -3 up to -9 they vary wildly among the programs. So one example is, how far back do you look for back references? Well, that is controlled to some extent by the quality setting, but a bunch of other things are as well. A GZip compressor might use the quality setting to dictate a bunch of its different parameters, because as we know, there are tons of decisions to be made in the deflate encoding process. What's interesting about BZip is that the -1 through -9 setting affects exactly one thing, and it's only the block size. There actually are no other places in the algorithm, really, where the quality setting would make any difference. There are a couple of places in stage 4 where the compressor can make its own decisions, but it's still rather difficult to see exactly what decisions it should make in the best case, or whatever. Like the flexibility that's afforded in stage 4 doesn't map easily onto some picture of what do I do to improve compression by leveraging this flexibility. So in BZip, if I use BZip-1 or BZip-9, that has no other impact besides choosing the block size for the BWT. But if you try BZip-1 and BZip-9, they do result in different amounts of compression. So the block size very clearly is an important parameter. It does have a high correlation to the resulting compression. So anyway, I choose a block size between 100K and 900K, and that gets encoded into the bit stream, so the decompressor knows which block size to use because that's relevant to the decompressor. But one thing to understand is that when I actually form the blocks is between stage 0 and stage 1. So if I'm using a 900 kilobyte block size, I batch up 900 kilobytes of RLE1 output to my 900 kilobyte block. That means that my block might actually represent more than 900K of input data, because RLE1 could have produced some compression. On the other hand, if RLE1 produced expansion, then it could turn out that my 900 kilobyte block actually corresponds to less than 900K of my original input. And that's because the blocks are formed after the RLE1 stage. And I guess the idea there is, if I'm performing a BWT with a 900 kilobyte block, I want to make sure I give the BWT legitimately 900K of data to work with. I don't want to make a 900 kilobyte block and then have RLE1 make it smaller, because first, that would mean I'm not getting the most effect out of my BWT, and second, it would probably make the compressor a little bit more clunky to implement, because if I know that all of my blocks are exactly 900K, I could reuse the same array over and over again to compute BWTs, whereas if the amount of data that ends up in the BWT changes at each step because of the block being packaged up too early, then I have to make new arrays or something, and that might be a little bit of a mess. So one way or the other, we make blocks, and then we feed those blocks through the BWT and the Move-to-Front transform. Now, we already know what the BWT does and what the Move-to-Front transform does, and we know that there's no decisions to be made along the way. Once you have a block of data, the BWT is pretty much always going to look exactly the same. So I'm not going to cover those in greater detail. Go back and look at the previous lectures for that. Here's an example just to walk us through the process. I've got this input here. I apply RLE1, and we'll notice in this input I do have a run of S characters, and that turns into this thing here. Now, this is just the value, the 8-bit value 00000011, so 0x03. I'm writing it as a numeral, which is a weird way of, it breaks our usual procedure of saying, well, look, if it's a readable character, then it corresponds to that actual character literal. No, this is an integer value. It's the number 3. So anyway, it ends up inside the RLE1 result. I then take the BWT. One thing to observe, to hold on to for later, of course, is that whatever set of symbols shows up in the RLE1 result, which could be a different set of symbols than was in the input, so there's one extra symbol in the RLE1 result. Whatever set of symbols shows up in the RLE1 result will be exactly the same set of symbols showing up in the BWT, because the BWT is a permutation of its input. So after the BWT, I then run the Move-to-Front transform, and as we know, the Move-to-Front transform transforms an input of a bunch of symbols into an input of the same length corresponding to indices on a stack, or on what it calls a stack. So refer back to lecture 5 to hear my grumpy diatribe about what I think a stack is versus what they think a stack is. And so when I perform the Move-to-Front encoding, I have to start off, as you recall from lecture 5, I have to initialize the stack at the beginning of the encoding process to contain every symbol that may occur. And the way I do that in BZip is I make a list of all of the symbols that occur in the RLE1 output and or in the BWT output, and I add all of those to the stack at the beginning of the Move-to-Front stage. And the way that I order the stack is I just sort the set of symbols numerically. So every symbol has a numerical value. I just add them to the stack numerically, with the one that has the smallest numerical value on the top of the stack. So unlike what I suggested in lecture 5, where in general for Move-to-Front coding, if you don't know which symbols you're working with, you could have your stack initialized to every possible 8-bit symbol. This Move-to-Front implementation uses a restricted stack that only contains symbols that actually appear. Now, it could be every possible symbol for all we know, but if it is a limited set, that is encoded directly into the stack. So we only have the symbols that actually appear showing up in the stack when I do Move-to-Front encoding. I'm allowed to get away with that because we're doing block-based encoding. So I can look at the entire block in advance and figure out which symbols appear. So as we can see in this example, when I perform BWT, this sequence does have a couple of runs of characters. So when I'm done with RLE1, I've got a couple of runs of R's in a row. I have these 4 S's in a row, and then the remainder of the S's are encoded with RLE1. I've got 2 R's in a row here, there's 2 R's in a row there, there's 2 more R's. So a bunch of cases of R's being in a row, but not really any other runs of the same character in a row. After the BWT, we can see the BWT has done its job pretty well. There are 3 Y's, there are 3 R's, there's a whole bunch of B's in a row, there's some E's, there's some R's, there's 2 S's, and then there's 4 R's. So the BWT has done its job pretty admirably. When I perform the Move-to-Front transform, runs of consecutive characters get turned into a single index followed by a run of zeros. So there are the 3 Y's. Here are the 3 R's. Here's my run of 5 B's, I think is this. And then there are the 4, I think this should be the 4 E's here. So anyway, you'll get a bunch of runs of zeros. What's nice about this is that now if I want to try and encode runs of consecutive characters in my BWT, well, to encode runs of consecutive characters in my BWT, I have to have an RLE scheme that can encode runs of literally any character, B or R or S or whatever. If I try to encode runs in my Move-to-Front, any run of consecutive characters in the BWT becomes a run of zeros in Move-to-Front, which means maybe now I can use an RLE scheme designed only to encode runs of zeros, and that's exactly what BZip does. One other note that I'll make about Move-to-Front encoding, which I already made in lecture 5, is that these are indices into a stack. What Move-to-Front generates are indices that basically represent, if the index is low, that means I've seen this character recently. So I think this one index here corresponds to this run of two S's, so a 1 followed by a 0. What this 1 is telling me is that I've seen the S recently. Recall that when I use a character, I move it to the front of that stack, to the top of the stack. And sure enough, I did actually see S 2 characters ago. So if the BWT contains patterns where you see a character and then you see it again in the near future, you'll generate a low index. And in data where that happens often, move-to-front will generally be biased in favor of lower indices versus higher ones. The reason that's beneficial is that results in this nice skewed distribution where some indices have lower value or higher value than others. So if I were to generate a prefix code based on these indices, there would be some symbols that get a short encoding and some symbols that get a long encoding. So my prefix code would fairly value them. Okay, but in any event, we perform these two transforms. We end up with this set of move-to-front indices that we're going to send into stage number 3. I should add that in the meantime, of course, the BWT actually produces two pieces of output. It produces this permutation here, but it also produces some index, as we know. The index is just kept over on the side. So eventually, the BWT index is going to be encoded into the block header when the block is actually written out. In the meantime, we just hold on to it. It doesn't participate in the remaining stages. It's written into the block header as a 24-bit value. So we know it's just a number, it's an index into a table, and we write it as a 24-bit number. And here we see the first example of the quartz watch taking advantage of its privilege of being so accurate that it can just throw away accuracy in other parts of the mechanism. So the maximum block size is this number of bytes, about 920,000. And this number is less than 2 to the 20, which means if I want to represent a BWT index is going to be an index between 0 and 921,599, the index only needs to be represented in 20 bits. And so if this were happening in the deflate scheme, we would represent the index in 20 bits. We might even use some weird meta-compression stuff, but we would probably use 20 bits or less to represent the index. And yet, BZip uses 24 bits. There is no way the index will ever be greater than 2 to the 20, and yet we still use 24 bits. Why? Well, my guess is that 24 bits lines up on a byte boundary, which makes it easy to debug. So we are wasting 4 bytes per block, because there's no reason we need those 4 bytes. We are wasting 4 bytes per block to make debugging easier back in the 90s. When the scheme was designed, those extra 4 bits helped the scheme designer debug their code. Or debug a BZip archive. Great, okay, so we now waste 4 bits per block. But 4 bits per 900K, hey, that's not such a big deal, especially since I am getting good compression. But notice how this is a scheme that doesn't try to economize that much, even though 4 bits isn't very many. We could still be saving those 4 bits. And we'll notice this happens a few times as we go over the bit stream. The bit stream is apparently rather inefficient in some ways that more have to do with just convenience than some sort of impossible to solve problem. There are easy ways to save bits that the scheme doesn't take advantage of. So after the move-to-front transform, let's keep up with the actual sequence of indices out of move-to-front. After the move-to-front transform, we throw that set of move-to-front indices into another RLE stage called RLE2, which is completely different from RLE1, except that it's obviously also an RLE scheme. The RLE2 stage encodes runs of zeros that appear in this move-to-front output. That's all it encodes. So RLE2 does not encode runs of any symbol except for the index 0. It just ignores all the other symbols and encodes them as literals. It only encodes runs of zeros. Before we do the RLE2 stage, we add an end of block marker, as we did with deflate, so that we can see the end of the block. The EOB marker will end up having to receive its own prefix code, of course, later, just like in deflate. And so maybe this is a feature that maybe becomes sort of universal. A lot of compression schemes have to use an end of block marker. So the RLE2 stage is sort of neat. I actually think as far as coverage of individual stages of the algorithm, we're going to spend more time on RLE2 than anything else. The RLE2 stage is interesting because although we've covered a lot of different variants of RLE, all of which really rely mostly on how we encode run lengths, we weren't able to talk about this particular variant back in lecture number 6 or lecture number 5 because we didn't know about prefix coding yet. And this RLE2 variant, the way that it addresses encoding run lengths, has to do with the fact that there's a prefix coding stage coming up right after it. So we might remember that back in the RLE lecture, really the biggest issue we've had with throwing RLE into a scheme is the fact that encoding run lengths can be sort of inefficient, and we have to make this trade-off that's always rather difficult. So for example, I could use a fixed width representation. I could store every run in 8 bits using an 8-bit run length, as the RLE1 stage does. But we noticed back in lecture number 5, that's difficult because if we're using a fixed width representation, we're sort of assuming that we're going to have lots and lots of long run lengths, which we don't generally have. I mean, we can expect typical data will not necessarily have really long runs. So to avoid a bias in favor of long run lengths, we'd rather not use a fixed width representation. We could use unary to represent the run length. So unary is great because unary uses a small number of bits to encode small numbers, so a short run length. But on the other hand, as the run length gets larger and larger, the number of bits goes up linearly, which is sort of a waste. So here is to encode the value 13, I have to use 14 bits, 13 1 bits and a 0. So unary has that inherent inefficiency. It's got a lot of inherent convenience, and it is efficient in some ways, but there is this inherent problem of, as your run lengths get really large, the number of bits does become sort of unreasonable. So one alternative would be to use a mixture of unary and binary. So as I've mentioned, my running example is always the number 13. If I want to encode 13 in a variable number of bits, but don't want to use 13 whole bits or 14 bits as I would in unary, I could split the difference by using a mixture of unary and binary. First, I say, here's how many bits my binary value is. It's 4 bits. And then here is a 4-bit binary value representing the number 13. And we observed, as this is doing, back in lecture 5, that actually, once I've told you that I'm using 4 bits, I don't have to send you all 4 bits, because you can pre-assume that if I tell you I need 4 bits, the most significant bit has to be a 1. So I can just ignore that 1 bit, and you can from context, it's implied, you can infer that the first bit is a 1. So I only send you the least significant 3 bits. That's what I'm doing here. So notice that I was able to take advantage of the fact that by knowing how many bits there are, it is pretty easy to actually omit sending over one of those bits. And some of that intuition factors into what BZip does, but BZip in RLE2 doesn't do this. It does not just send bits to the bit stream. When there's a run of a bunch of zeros in the move-to-front index stream, it doesn't just send bits to the bit stream, which is sort of what deflate would do. So we know that deflate sort of mix together symbols that get encoded with prefix codes and just bit offsets that get written directly out to the bit stream intermingled with those prefix codes. What BZip does is tries to keep everything in terms of symbols that can end up having prefix codes. So if I have a sequence of indices like 1, 5, 6, 0, and let's do 3 zeros in a row, 7, 9, 1 again, 5, well then I want to encode this run of zeros efficiently using some version of RLE. The idea though is that when I'm done, all of these indices are going to get run through prefix coding, and each of them is going to receive, I don't know, some prefix code or something like that. What I could do is, yes, encode this with a run length that just gets dumped directly into the bit stream as bits, but then I have to have some way of telling the decompressor that that's what I'm about to do. I have to tell it, oh, a run length is coming up. I have to use some symbol for that. That is possible. Deflate does something similar. What BZip does, though, is what comes out of the RLE2 stage is entirely a bunch of symbols that can then receive prefix codes. No raw bits get generated. Instead, a binary representation gets generated that gets encoded in regular symbols. And so we actually create new symbols that we can use to encode our run lengths. So in this case, I have a run of length 3. I could represent that run of length 3 using 2 bits in binary. So it's a bit more complicated than this, but basically what we can come up with is a way of adding that binary encoding of the run length directly into this stream of symbols to replace the run of zeros. And I encode it into the stream of symbols by using a special symbol to represent the different bits that could occur in the run length, the bit 0 and the bit 1. I observe at this point that, of course, we didn't have to have a debate about how to encode run lengths specifically for deflate, because deflate uses an LZ scheme, LZSS, and LZ schemes sort of have RLE built into them. So we don't have to worry about this issue of how do we tack on RLE to something else. I mentioned earlier that in BZip, we were going to have to worry about that problem because BZip doesn't use an LZ scheme. So although deflate doesn't have to worry about encoding run lengths, we have some precedent to think about the case where we're encoding a mixture of actual prefix-coded symbols and arbitrary bits into our stream. But BZip doesn't do that. Instead, the RLE2 stage is encoding runs of zeros and only runs of zeros. And it encodes them using a run length in base 2. So we don't have the same inflation we have with unary. And the way that run length is encoded is by adding 2 new symbols to my symbol stream. So my symbol stream before this consisted of all the move-to-front indices, which at this point start at 0, although I'm going to get rid of runs of zeros, as well as the end of block marker. The RLE2 stage adds 2 new symbols, a symbol which at this point will be numbered 256, which is called run A, and 257, which is called run B. I'm going to refer to them for brevity as RA and RB. And the RA and RB symbols are used to represent single bits in the run length. And since they are distinct symbols, it's really easy to distinguish a bunch of bits of a run length from other symbols. And if that doesn't make any sense, I've got a few examples. So this first example isn't exactly what BZip does. What BZip does is more complicated. I'll get to that in a minute. I just want to use this to sort of ease us into the idea. So suppose I've got this sequence of move-to-front indices, 1, 3, 2, and then 8 zeros, and then 9, 107, and then 5 zeros, and then 3, 6, and then 10. Well, I can observe that this run of 8 zeros, if I encode the run length in binary, the run length 8 is 1000, okay? And this one, the run length of 5, is 101. So what I do is I take that binary encoding and I write it out using these substitutions. So RA is a 0-bit, RB is a 1-bit. So I take that number, which means 1000 would become RB, RA. So 1000. And then I take that encoding, that 4-bit, that surrogate for a 4-bit number, and I encode it into my bit stream. I just dump it in where the run of zeros was, least significant bit first. So 0, 0, 0, 1. So now it's a sequence of RAs and RBs. And then I do the same thing with my run of length 5. So this becomes least significant bit first, RB, RA, RB. And then when I'm done, I take this sequence of symbols, so it's a mixture now of indices and the symbols RA and RB, and I send it off for prefix coding. And you'll observe if there are lots and lots of runs of zeros, there will be lots of occurrences of RA and RB, so maybe RA and RB get a very small prefix code. Maybe they do. And we're probably relying on that because we're trying to ensure we have runs of as many zeros as possible and that we encode them as efficiently as possible. One benefit of this that the previous slide does sort of mention is that because I'm using separate symbols to represent my run length bits, so RA and RB are surrogates for 0 and 1, it's really easy when you're scanning through the symbol sequence to know how many bits go with each run length. There will never be 2 runs of zeros in a row. It wouldn't make any sense to have a run of 5 zeros followed by a run of 4 zeros because that would just be a run of 9 zeros. There will never be 2 runs of zeros next to each other because that's just one long run of zeros. And therefore, I don't have to worry about RAs and RBs, separate encodings bumping up next to each other. If I'm looking at the sequence and I see a bunch of RAs and RBs together, so this is a group of 4 RAs and RBs all together, I know that these 4 bits represent one run length, and it's going to be 1000. So that's the idea. These separate symbols make it really easy to know how many bits are in your run length because they're separate symbols. And when you hit something that isn't RA or RB, you know you've reached the end of the run length. Now, BZip doesn't do exactly this. So this is a little bit too simple. BZip does something more advanced that relies on the same intuition that I brought up a few minutes ago. So I brought up the fact that when we're using that mixed unary binary representation, I could encode the value 13 like this. So this is the binary value for 13. This is the unary value for 4. But I don't need to do this because when you know you're going to have 4 bits, you can assume the most significant bit is a 1. So I can knock off, I can save 1 bit using the information that I gather from the number of bits that I need. I can do exactly the same thing with this RB and RA representation. I can chop off the most significant bit. I have to be a little bit careful though because there's one degenerate case that would get in my way, which is what if I have a run of length 1? So if my run has length 1, well, by the encoding I was using on the previous slide, a run of length 1 would just be, okay, the binary value for 1 in base 10, we'll just try this out, that's 1 in base 2. So I'd encode that as just RB by itself, using this simple representation. If I chop off the most significant bit, well then I've got 0 bits. Okay, I can't encode a run with 0 bits, because then nobody would know there was a run at all. So I have to work around that case. On the other hand, I'll never see runs of length 0. Because if I have 0 zeros in a row, I just write out nothing. So I don't have to worry about runs of length 0, but I do have to have runs of length 1 be representable in at least 1 bit. So BZip works around that with a pretty simple technique, although this slide is pretty mathematically dense. So here is the formal definition of what happens, specified with arithmetic definitions. If you actually implemented this in C or C++, you'd probably use a bunch of bitwise operations. You might use a combination of a shift, a bitwise not, or a bitwise complement and a bitwise and, or something like that. But in this case, it's stated with sort of arithmetic terms. You also, of course, would use bitwise operations to compute this thing. You would not actually try and compute a logarithm in base 2 with, I don't know, floating point arithmetic. So what I want to go through is just what this means intuitively, which is if I have a run length, so suppose, let's not use 8 because we already tried that. Suppose I have a run length of 4. Okay, my run length is 4, so 4 in base 10, if I encode that into binary, that would be 100 in base 2. The procedure that BZip uses to encode the run in RLE2 is we first take the run length and add 1 to it. So it's now going to be 5, and 5 is going to be 101. And then we chop off the most significant bit of that. So we basically compute the binary encoding of n plus 1 and chop off the most significant bit. And then we encode the remaining bits, least significant bit first, into the stream. This means that if I have a run of length 1, okay, well, the run of length 1 would normally be encoded into a 1-bit, but I first add 1 to it, so now it's 2, and then I encode that in binary, that's 10, and then I chop off the most significant bit. So runs of length 1 get encoded with a single 0-bit. And that's it. So really all I'm doing is just adding 1 and then chopping off the most significant bit to get rid of that special case where if I was just chopping off the most significant bit without adding 1, I would have 0 bits for a run of length 1, which would be problematic. So when I'm done, I end up with this procedure. So this is the actual version that BZip uses. The simplified version from 2 slides ago is too simple. BZip uses this version instead. So if n equals 8, the binary encoding would be 1000, but instead I add 1, which means I get the binary value 9, and then I chop off the most significant bit. So the binary encoding is 001. This goes into the stream least significant bit first. So the 1, which is RB, goes first, then I've got RA, then I've got RA. And if I try to encode the binary value 5, okay, well, but 5 actually, I add 1, so I get 6. 6 is equal to 110. I chop off the most significant bit, so I get 10. So I encode that as RA, which is the 0-bit first, RB, which is the 1-bit second. And again, recall that when you have a run of only 10, that just turns into, okay, so wait, a run of length 1, so I add 1 to that and I get 2. That ends up being 10. I chop off the most significant bit, so my run is encoded with just a 0-bit. And the 0-bit, remember, is RA. So if I have a run of only 10 in a row, it gets encoded as a single occurrence of the symbol RA. So the key thing to remember is we put least significant bit first. All right, so just to recap our example, here's our original data. As of the end of the move to front stage, it was this. Then I add my end of block marker. There it is. And then I perform RLE2. So here's my run of 2 zeros. Okay, wait, so the run length of 2. Well, I add 1 to that and I get 3. And so 3 encoded into binary is 1 in base 2. And then I chop off the most significant bit. So all I have is a 1-bit. The 1-bit is RB. So here's my run of length 2. It is encoded as just RB by itself, just a 1-bit. And then somewhere else here, I do have a run of length 1. Notice, as I mentioned on the previous slide, that gets encoded into a single occurrence of RA. In the meantime, I've got other runs of different lengths. So here's a run of length 4. There's a run of length 3. The run of length 4, I think, gets encoded into RB, RA. The run of length 3 gets encoded into 2 RAs in a row. Then I've got a run of length 3 again. That's going to be 2 more. 4 RAs in a row, and so on. So hopefully you can see that happening. Notice that in general, I am achieving a reduction in the total number of symbols. So although I've increased my symbol set, this run of 4 zeros ended up being 2 symbols when I was done. This run of 3 zeros ended up being 2 symbols, and this run of 1 zero stayed at being 1 symbol. So I don't experience any expansion in terms of the total size of the stream, although it is possible that going from having a single symbol that I represent in, let's say, groups of 3 to 2 different symbols that now alternate could have some effect on the efficiency. Although I will present at the end of the lecture a sort of case study to try and analyze this with an anecdotal sample input. Okay, so then after RLE2 is done, I have this sequence of symbols that now includes various move-to-front indices. I've got the special symbols RA and RB and the special symbol EOB. And then I throw that into a dynamic prefix coding stage. So obviously that means if I'm going to generate a code, I probably will generate a Huffman code, but formally this is just prefix coding. The symbol stream is then encoded over the set of symbols 0 through, or actually that should say 0 through 258. It depends on how many symbols actually appear, as I'll mention in a minute. But nominally, at least in the documentation, you are supposed to assume that after RLE2, the number of symbols that could occur, well, there will no longer be the 0 index because I've gotten rid of all the 0 indices and replaced them with RB and RA. As I mentioned earlier, initially we number RA and RB to have the values 256 and 257, and the EOB marker has index 258. So at least nominally, what comes out of RLE2 is a set over the alphabet 1 through 258, although we'll notice almost immediately on the next slide, we renumber the set of symbols. So theoretically, at least, there are this number of possible symbols showing up after RLE2. But recall that when we perform the move-to-front transform, we initialize the stack only to contain symbols that actually occur. So the stack might not contain every possible 256 or each of the 256 possible 8-bit symbols. That means if the stack only has, let's say, 12 things on it, there will only be 12 different move-to-front indices that ever show up, not all 256 that could exist in the worst case. So after the RLE2 stage, before we begin prefix coding, we renumber the set of symbols. And you'll observe that previously run A and run B had high numbers, and now they're for some reason being moved to low indices. And furthermore, move to front index 1 is being renumbered as 2, and move to front index 2 is being renumbered as index 3. That's a bit convoluted. Yeah, okay, but I mean, compared to the code length table from Deflate, this isn't so bad. But you can see, as we get closer and closer to dumping things into the actual bit stream, it appears as if we sort of have to make this form of compromise. Sometimes arbitrary renumberings just seem necessary, I guess. So anyway, the renumbering we perform is we renumber RA to be 0, RB to be 1. Then we already know which set of move-to-front indices could possibly occur. So depending on how many symbols were in the output of the RLE1 stage, the move-to-front stack was initialized to contain only those symbols. And therefore the move-to-front, the set of possible move-to-front indices is actually just some value n, or it's n plus 1 because the 0 index previously could occur. But there are only going to be n plus 1 possible indices that could appear in the result of move-to-front. So 0 through n, although we've now eliminated the 0 index in favor of these runs. And so we renumber the symbols to accommodate only those move-to-front indices that could occur based on the size of the stack when move-to-front began, followed by the end-of-block marker, which gets the next available index, which we don't actually know in advance because it depends on the size of the move-to-front stack. So if there were only n distinct symbols in the input, then the stack was initialized to only have n entries, so only these indices could have actually appeared. And that means that in our renumbered symbol set, we're removing all of those indices bigger than n minus 1 that would never have appeared. Now, one question which isn't relevant to this. So whether or not all of these indices, so 0, 1, 2, 3 up to n minus 1, whether or not they actually appear in the move-to-front output, if the stack had size n going in, there will be symbols available for all n of these indices. And remember that the 0 index gets removed by the RLE2 stage. So even if index 3 never appears, it still does get to have a prefix code, or it still gets to participate in the code length table and whatever else. It still gets an index in this symbol set. One question, which is therefore not relevant to this specifically, but a question you should think about relevant to move-to-front encoding is, if I start move-to-front encoding with a stack of n symbols, and I guarantee you every symbol does occur at least once, is it possible for a particular index to never appear in the result? So even if each of my n characters does appear, so each of the n things that were initially in the stack does appear, is it possible for there to be an index that never actually shows up? That's something to mull over before the exam as well. So either way, I have this revised, renumbered set of symbols. I then look at the contents of the symbol stream coming out of RLE2. I figure out the frequency of each symbol, and I generate a Huffman code. Okay, and so then I've got this code length table, and just like in Deflate, and as we'll see, a pretty standard feature of prefix code-based schemes is that I don't send the decompressor my actual set of codes. Instead, I generate a set of optimal code lengths, and then I use a standard algorithm to generate the code from that. So that means I can just send the decompressor my code length table, and it can regenerate the code itself. The algorithm I use to generate code lengths is the same one we've seen over and over again, and in fact the same one used by Deflate. The maximum length of the encoding for a specific symbol is limited to 20 bits. Deflate uses 15, BZip uses 20, but both ways, in case Huffman coding sends you back a code that's too long, it's your problem to fix that, either by not using Huffman coding, for example, using the package merge algorithm, or by fixing up your code tree after the fact. So codes are limited to 20 bits at most. That's the maximum length you can see. I'm not going to go into great detail about exactly how the blocks look in terms of the bits in them. Because I'm not going to do that, it's tempting to look at the overview that I give and say, wow, BZip is so much simpler than Deflate. Okay, that's going to be false. I have written my own BZip compressor for the sake of knowing what I'm talking about for this lecture, and I can tell you that, okay, there are certainly parts of the Deflate bitstream that are an acquired taste, but there are also parts of the BZip bitstream that are like that. Ultimately, in the grand scheme of things, they are both very convoluted. The formats are very convoluted for both, and so I don't want us to think about Deflate as being the messy one. They both are a bit of a mess internally. There is a question of, which things are considered more odious, but that's a matter of, I guess, each person having their own personal taste in that matter. So I'm not going to talk about it at a low level, but take my word for it. I think there are plenty of places in the block header where it's a bit of a weird mess. It's a different kind of mess, I guess, because Deflate, for example, is a lot less squeamish about storing things at the bit level, whereas in the block headers for BZip, there's a tendency to want to keep things at the byte level to the extent possible. But otherwise, yeah, it's still a bit of a mess because you're storing lots of data and you want to store it efficiently. Some aspects I won't go into greater detail about, but that I do want to mention, some curiosities about the block header, is that within each block, you're actually allowed to have more than one prefix code defined. So you're allowed to generate up to 6 different prefix codes and then switch between them as you encode the block. And you have to tell the decompressor when you're switching so that it can switch between them too. My understanding of why this is a good idea is, remember that in BZip, unlike in Deflate, the compressor has no authority to decide how big the block is. The block size has been selected in advance. So if you have an input file which exhibits some kind of internal structure where the file has patterns that repeat at a macroscopic level, so for example, the first, 53 kilobytes of the file has a particular internal structure, the next 10K has a different structure, and the following 30K has a third structure, and then we're back to that first structure again. In Deflate, you might be able to break up the file into blocks by observing. If you had some way of figuring this out, you could observe these different patterns and break it up into blocks for each pattern. But in BZip, you can't because the block size has been pre-selected. You must make perhaps all of this one big block. So if you want the ability to optimize to use a different prefix code for each part of the block, and you have the ability to recognize these boundaries, which is not easy, so I mean, maybe this is a theoretical concern, you can generate a prefix code for each subset of the block and store them all in the block header and then tell the decompressor when you're switching between them. Okay, so that's a feature that I consider to be relatively useless. I mean, there are cases where it's useful, but it seems like we're defining a lot of extra infrastructure for something that might not have that much of a payoff. Because generally speaking, Huffman coding should still be pretty good across the entire block using the same code for everything. And even if the file had some internal patterns originally, does it still have those patterns after you've taken a BWT and applied RLE2 to the move-to-front result? Like, really? Are you going to be able to identify these distinct patterns? Maybe you are, I don't know. But in any event, event, although this feature seems a bit clunky and I don't see where I would use it, I'm willing to, live and let live. I'd say fine. We can have extra features that I don't use in the block header, just like in deflate. There's all sorts of extra things in deflate that I might choose not to use. I could choose which block type to generate. I could never generate block type 2 in deflate, for example. What's sort of weird about these features in BZip is you are sort of required to participate. So if I want to use one Huffman code for the entire block, I can do that. But I am, for some reason, although I can define up to 6 prefix codes, I'm not allowed to only define one. I am required to define at least 2. So if I want to use only one, I have to, I don't know, encode the same one twice? Deliberately encode redundant information because of this arbitrary requirement of using at least 2? That's ridiculous, frankly. Even if I use only one, I must provide 2. And here we go again with BZip basically gratuitously wasting space. Because the quartz crystal is so powerful, BZip can afford to just say, yeah, make the block header just bloated as you want to enable these extra features that nobody might ever use. And it goes further. Because we have the ability to use a different prefix code to switch between prefix codes at regular intervals, you are required to tell the decompressor which prefix code you are using for every 50 bytes of input. So there are 6 different potentially 6 different prefix codes, and you are required to encode into the block header a so-called selector for every 50 bytes of input data. So each 50 bytes, you have to give an index for which prefix code am I going to use for this 50 bytes. And that means the block header has to contain a vector of indices for every 50 byte group of data within the block. That's actually quite a bit of data that I have to add for every single block, if my blocks are of size, for example, 900K. So one extra index per 50 bytes, even if I intend to use exactly the same prefix code for every single block. I would encode the same index over and over again for every 50 byte group of data. Again, here we go, wasting space. But it's not over. So as with gzip, there is a CRC checksum at the end of the file. That can be helpful for the decompressor to verify that what it decompressed apparently did match the original input data to some extent. So one good check just to verify that the decompressor didn't make a mistake, or that, to verify the file wasn't corrupted. But in BZip, in addition to having that at the end of the file, every block has its own 32-bit CRC value. Of course, having this can be helpful for error detection, so you can, if your file gets damaged, you can figure out which blocks are intact and which blocks aren't. But of course, it's also wasting 4 bytes per block. If you want, I would argue if you care about error detection that much, just use an underlying format, like an archival format, either on top of or inside the compressed BZip representation that does that error detection. Don't require everybody using BZip forever, even people that don't care as much about error detection because they're not doing archival or something. Don't require all of them to have 4 bytes extra per block. But whatever, 4 bytes out of 900K isn't so much. But this is sort of piling up. We are using a lot of extra bits that we don't have to, unlike what deflate does, which is to scrimp and save, to make that mechanism as precise and intricate as possible, because when you're designing a mechanical watch like deflate, you need all the accuracy you can get, whereas BZip with its quartz crystal can just throw accuracy away. And then we've got this. So just like with other formats, there's a magic number at the beginning of the file, so somebody looking at the file in a hex editor can maybe get some idea of what kind of file they're working with, and so that the decompressor, as a very basic format check, can verify that you're asking it to decompress an actual BZip file. So there's a magic number. Okay, that's a good idea. But in BZip, not only is there a magic number at the beginning of the file, there's a magic number at the beginning of the footer at the end of the file, and a magic number at the beginning of every single block. Contrast to deflate, where every block has to begin with the 1-bit is last flag and a 2-bit encoding of what type of block you're using, and that's it. So each block header in deflate is 3 bits long. In BZip, every block begins with a magic number. Oh, okay, that's not so bad. What kind of magic number? Is it 1 byte? Is it 2? Nope, it's 6. You use a 48-bit magic number at the beginning of so there's 6 extra bytes that I'm just throwing away per block. I have no idea why we need this. This is ridiculous. I know that 6 bytes out of 900K isn't so bad, but across all of these things, I've used a lot more than 6 bytes. I could do better than that. But BZip is a rock star. It does its job so well that it can afford to just throw its money away, I guess. So we won't go into more detail about exactly how that stuff is encoded, but the documentation's out there. In general, there tends to be, I found, better documentation for BZip than gzip. So I do want to talk about the data that has to go into the block header at a macroscopic level, so the actual important stuff, not the extra checksum or the extra magic number. So the block has to contain, in addition to the actual encoded bit stream, so I mean one of these days I'm going to have this sequence of indices and I'm going to want to turn it into a sequence of bits, so some prefix code or whatever. I want to send this bit stream, the result of taking the RLE2 output and encoding it with a prefix code. I want to send that out to my file. In addition to this encoded bit stream, I also need to send out the 24-bit encoded BWT index, which could be 20 bits, but we have to use 24. I also have to send out, I have to tell the decompressor which set of symbols occurred in my input. Remember that the move-to-front stack was initialized only to the set of symbols that actually showed up in the RLE1 output, which means I have to tell the decompressor which symbols those are so it knows how many symbols I'm working with. And of course, I have to somehow convey the code length table for the prefix code. And the prefix code will be over the n possible move-to-front indices, or actually it'll be n-1 because the 0 index won't be present, plus the RA and plus the RB symbol and plus the EOB symbol. So of course the prefix code also includes those. So I'm going to do this thing first. How do I tell the decompressor which possible 8-bit symbols occurred in the RLE1 output? Which things do I use to initialize my move-to-front stack? I could get into meta-compression tricks like the CL code in Deflate, but BZip does something relatively simple, which is, I think, reasonably efficient. It's a clever way of viewing the problem that's pretty clean and streamlined, which is, well, there are 256 possible 8-bit symbols. And I could just send over the answer, yes or no, is each of these symbols present? So what we're talking about now are the set of 8-bit symbols in the RLE1 output. We're not talking about run A and run B or EOB just yet. So there are 256 possible 8-bit symbols. What I could do is send the decompressor a 1-bit flag for each of them. So we'll call this the present bit. If the present bit is set for symbol 0, that means symbol 0 does show up at some point. And then symbol 9 does show up, symbol 15 does show up, symbol 23, symbol 24, symbol 20, whatever. Okay, so I now know which symbols occur, and if I know how many symbols occur, I also know which move-to-front indices could occur, because the number of possible move-to-front indices is equal to the number of symbols that occur in the RLE1 output. So I could just make a 256-bit sequence where bit I, so in this case bit number 1, represents a flag of is symbol 1 present or not. Now the issue with this is all right. This is only going to be 256 extra bits, and given how many bits we've already wasted in the block header, I guess 256 more isn't that big of a deal, but maybe we can economize a little bit on this. Notice that there are going to be, maybe if my set of input symbols is sparse, there could be large blocks of input symbols that are not present. So this entire block of 16 input symbols is not present. So what I could do is one more layer of meta-compression, which is for each, I could group the symbols into blocks of some size. In this case, I'm using blocks of 16 symbols at a time, and I could set a populated bit for every block. The populated bit is set to 1 if any of the present bits of that block are set to 1. So in this case, the populated bits, I think the slides are going to say this, the population bits would be 1101. So this one is populated, so is this one isn't, this one is. And then what I do is for the blocks that are populated, I send over all 16 present bits. And then you can unpack the block that way. For the blocks that are not populated, it's understood that all the present bits are 0, so I don't send them at all. So what I would do is first send over the population bits, and then after all the population bits are sent, now this is only 64 symbols, so there's only 4 population bits, but for all 256, there would be 16 population bits. After I send all 16 population bits, which is 2 bytes, I would then send over the present vector, which would be 16 bits, so another 2 bytes, only for those blocks that had a population bit set to 1. And so this doesn't optimize away cases where much of a block is set to 0 or where all of a block is set to 1 or something, but it does help to condense down sort of obvious cases of a whole bunch of zeros in a row, of 16 or more zeros in a row. Now, in the worst case, of course, maybe in my input, every possible 8-bit symbol did appear. I still have to send over all these vectors. So if every 8-bit symbol appeared, then every single block's population bit is going to be set to 1. But I still have to send the whole thing over. So I have to send over all 16 population bits, followed by all 256 present bits. So I end up wasting 272 bits. So in blocks that have a very diverse array of possible symbols, I use maybe up to 272 extra bits, or I waste some of those bits. On the other hand, in cases where the block contains relatively few different symbols, I can achieve a little bit extra compression here. So anyway, I end up with this code length table. Now, by the time I get to the code length table, remember that I have a set of up to 258 symbols, which not necessarily always 258 symbols, because in some cases, the possible set of move-to-front indices is smaller than 256. But in the worst case, there are up to 258 possible symbols. There will be RA, which is my 0 bit for RLE2, RB, then move-to-front index 1, then move-to-front index 2, and so on. I guess this would be move-to-front index, 255? And then here's the EOB. So I could have a code length table of up to this many things. And now the question is, how do I encode that code length table? So the issue here is the code length table could even contain 0 length codes, although this is an example. It probably wouldn't contain this many zeros because of the way move-to-front encoding works. So I encode my code length table by encoding the very first entry, so that would be this thing here, as an absolute 5-bit value. So I use 5 bits because the maximum code length is 20. So to encode the number 20, I would need 5 bits. But what's weird about this is, of course, well, 2 to the 5 is equal to 32. So if I'm going to use 5 bits, why not allow a maximum code length of 32? Give me a break. But no, we allow 20, and so we have to use 5 bits. If I required the code length to be at most 6 or 15, then I could use 4 bits. But no, we use 20, so we use 5 bits. Okay, whatever. So I write out a 5-bit value. Then I encode every other entry of the table using delta compression. So this would be, I write out the absolute length 3, then I do a +0, then I do a +2, then I guess this would be a -5 in the event of a 0 length. Although, as I said, this is an anecdotal example. 0 lengths seem to be relatively uncommon. In the analysis I've done, they seem to be relatively uncommon. Because it depends on a certain weird property of move-to-front encoding that is unlikely to occur. So to encode my delta values, I use this very simple delta compression scheme, which is I need to be able to walk both up and down. The deltas could be negative, they could be positive. And so I encode delta by counting it off. If I want to encode the delta value +3, I would do +1, +1, +1, and stop. If I want to encode -3, I would do -1, -1, -1, and then stop. If I want to encode the value 0, then I would just say stop. So I stop before counting off anything. So this delta compression scheme allows me to count up, it allows me to count down, and so I can encode both positive and negative deltas, and in general, the representation of a delta value increases in length as the magnitude goes up. So longer deltas are more bits, smaller deltas are a smaller number of bits. You might remember this exact scheme, this exact table was our very first try at a variable length delta encoding from lecture 6, from the delta compression lecture. Our very first try, we tried this out. We observed that it did produce a beneficial result. We were able to achieve some compression, but then we stared at it for a minute, and about 4 slides later, so we're on slide 46 in this lecture, by slide 50 or so of lecture number 6, we had a better delta compression scheme because we were able to observe that this is actually full of some redundancies. There are easy ways to save a few bits on this and result in a more compact encoding of deltas. So in our very first experience with delta compression, we were able to come up with this scheme and very quickly improve upon it. And you'd think the designers of BZip, who are compression experts, would have done the same thing, but they didn't. And so in BZip, we use this basic scheme even though it's inefficient. Then again, BZip's a rock star. BZip is a quartz watch. It's got so much compression advantage already that it's able just to throw its money away, and here it goes doing that again. So anyway, it uses that encoding scheme. Whether it could have done better or not is one thing. It still gets a pretty good result. If we think of, so this is going to be an anecdotal case study. I've chosen an input. I've chosen it with a certain bias, which is why it's anecdotal. I want to spend the next few slides talking about the performance of BZip and the particular parts of BZip on this one input. This would be the complete text of A Tale of Two Cities. We've seen this over and over again back in lecture 2. We looked at this, basically the same table, a benchmark of of the size of the original piece of data versus the sizes after compressing using deflate, BZip, and LZMA, the big three. I want to use this piece of input data because first, it's even if you don't want to read the actual book, it's sort of intuitive what it contains. It's English text. It's a text file full of English words for the most part. And also because the complete book is less than 900K in size, which means that I can encode the whole thing into one BZip2 block, which makes analysis a bit cleaner. If it got split across multiple blocks, we have to think about the impact of having to recreate the Huffman code across block boundaries or something, which I don't want to do. So here I used my own BZip compressor to encode this thing, and then I instrumented the result, so encoded it into one 900 kilobyte block using one Huffman code. The real BZip compressor might use multiple Huffman codes for all I know. I used one Huffman code, and I want to show off some statistics of what I observed about the specific, especially the RLE2 stage, because I feel like that's the biggest mystery in all of this, since we know a bit about Move-to-Front and BWT and Huffman coding already. So because we know it's English text, we already know a bit about the behavior of English text under the influence of RLE. So I'll go backwards. Here's the code length table. So after I encode the entire block, run it through everything, including RLE2, I generate my Huffman code, and the symbol RA gets a code length of 2, which is pretty rare. So when you have this many symbols, in general, if I hadn't done all of the other compression first, so Move-to-Front followed by RLE2, having a single symbol out of an alphabet this large getting a code length of 2 means that that symbol occurs about 25% of the time. So that's a pretty significant advantage. RLE2 is producing a lot of RA symbols. Similarly, RB is showing up with length 4. Move-to-Front index 1 shows up with length 2. That shouldn't surprise us too much because we know in general it tends to be the case with long inputs that recently seen characters tend to occur again. And that probably occurs in English text a lot because there are certain characters in English text that are just very common and therefore show up very often and very close to each other. So for example, think about the character I inside the word indices. There are only 2 characters between the 2 occurrences of the letter I, and that means that I will show up relatively recently in the stack. It'll have a relatively low index. So it shouldn't surprise us that code lengths tend to be, generally speaking, go up as the indices go up. And the least common indices are the very large indices, because it's very unlikely you take a character you haven't seen in a very long time and use it again. And then, of course, the end of block marker, which we know occurs only once, is tied for getting the longest code length. Now, the actual numbering of symbols in the encoded bit stream, of course, would be this would be numbered as 0, this would be numbered as 1, this would be numbered as 2. I've numbered them for the sake of us understanding what they mean. But on slide 51, we talked about the actual numerical ordering of symbols after the RLE2 stage, where RA gets assigned 0 and RB gets assigned 1, and so on. After I do the RLE1 stage on the initial input, I get this breakdown of runs. And one of the reasons I like using English text as input, not only is it intuitive, but we know a lot about what kinds of behavior to expect in English text. We know already that in English text, we're unlikely to see runs of longer lengths than maybe 2. Inside of a word in English, I don't know of any English words that contain runs of length 3 or longer. The text of the book does contain some runs of length up to 8. I took a look at what they are. For the most part, they are formatting related. So the book, although it's a book in English, it is a text file that contains a table of contents and chapter headings and things. Because it's a text file, the formatting is all done by just adding extra spaces or little punctuation marks to delineate stuff. And so when I have 8 spaces being used to perform indentation, that's going to be a run of length 8. When I'm forming a table of contents where I want to line stuff up nicely, where like I want to say stuff like chapter 1, and then I have chapter 1 showing up at page 50. Chapter 2 shows up at page 70 or something like that. I'll put spaces here. So I'll see runs of spaces in that way as well. I might format my table of contents by using dots and not spaces. Okay, whatever. So I could have runs of the same character, and we have a modest number of runs of length longer than 2. Remember, though, that in RLE1, only runs of length 4 and longer actually have a run length that gets encoded. All of these just get left as literal data. So in RLE1, there are very few runs of consecutive characters in the grand scheme of things. Most runs have length 1. And part of that's because, yeah, we know we're encoding English text. English text doesn't tend to have long runs. However, once I've done the RLE2 stage, so what I'm counting on this slide and the next few slides are runs of zeros. Remember that RLE2 doesn't care about runs of other symbols, just runs of the zero index out of the move to front stage. If I look at all the runs of zeros that I see in after RLE2, 48,000 runs of length 1. Okay, so there are lots of zero indices just sort of scattered around randomly. But there are 17,000 runs of length 2, and still in the thousands if I look at runs of length 10 or greater. So there are about 1,200 runs of length 9. There are a whole variety of different runs of length 10 or greater. So there's like not just 10, 11, 12, but it goes up to the hundreds and the thousands in length. If I look at all the runs of zeros, the average length of a run was about 4.1. The median length was 2, so the majority of runs are length 1 and 2. The longest run, though, had length 5,658. There actually were 2 runs with exactly that length. And that's likely the result of the BWT and Move-to-Front identifying certain extremely common patterns and capitalizing on that. The next longest run length after 5658 was, I think, in like 1800 or something. So it's not like there are too many runs longer than that are in the thousands in length, but there were at least 2 runs that were in the thousands of characters in length. And the thing is about this, though, if I look at the number of runs, yes, it looks like the number of runs drops off as the runs get longer, but I have to consider that the efficiency of RLE tends to go up as time goes by. Encoding a long run tends to be much more efficient than encoding a short run. And we already saw RLE2 is pretty good at encoding even short runs. Even a run of length 1 gets encoded into only 1 symbol. So it went from being a single zero index to being a single occurrence of the symbol RA. So even runs of length 1 are encoded pretty efficiently. So I should talk not just about how many runs I saw, but how many bits I need to encode those runs. So if I have a run of length 1, well, again, that gets encoded into a single occurrence of just RA. As we saw a few slides ago, RA is 2 bits in length in this particular input specimen. So it's going to end up being the bits per run for a run of length 1 is 2. A run of length 2 gets encoded into a single occurrence of RB, because recall that, okay, the binary encoding of, so I have 2, but in RLE2 I first add 1 to the number, so I get 3. That encodes into 1, 1. Then I chop off the most significant bit, and then I'm encoding this 1 as RB. RB, if we go back a few slides, RB has a code length of 4. So that means that I end up using 4 bits per run to encode a run of length 2. So that means if I encode all of the runs of length 1, then it ends up using, well, there are 48,000 of those runs, so I use about double that, so 97,000 total bits to encode all the runs of length 1 together. If I encode all the runs of length 2, I end up using 70,000 bits, so I use fewer bits because there are, of course, fewer runs, even though the runs, I use more bits per run. But notice that as things go on, the number of bits per run increases, but not that quickly. And actually, there's even this inversion, which you'll have to think a bit about. It has to do with something that in Deflate could be viewed as the beginning of a feedback loop. It's not a feedback loop here because I had no decision-making ability back in RLE2. The issue is that because RA, the symbol RA, has an encoding length of 2, and the symbol RB has an encoding length of 4, well, that means, so remember that RB is conceptually sort of a 1-bit. And RA is conceptually sort of a 0-bit. When I encode run lengths, that means that the number of bits I need to encode a particular length is now sensitive to the particular distribution of 0 bits and 1 bits that I'm encoding. If my length tends to contain a whole bunch of 0 bits, so remember that if I encode the length 7, well, 7 plus 1 is 8, and the binary encoding is 1000, and then I chop off the most significant bit. So the encoding is going to be RA, RA, RA. And RA is 2 bits, so I need 6 bits in total. On the other hand, if I want to encode 6, well, 6 plus 1 is 7, and that equals 111. I chop off the most significant bit, and then I'm encoding 11, which is 2 RBs. And even though it's fewer symbols, so even though in this example I'm encoding 3 and in this example I'm encoding 2, RB has encoded into length 4, which means that 6 ends up requiring 8 bits, whereas a run of length 7 requires only 6. That's a weird inversion, but it's not a feedback loop, because unlike in Deflate, where if I find myself with a certain back reference getting a short encoding, then it could have been if I'd gone back in time and chosen a different combination of back references, I could have improved or decreased compression efficiency. That's a feedback loop because I've got two sets of decisions fighting with each other. In this case, although this is a weird inversion, it's not a feedback loop because if I see a run of length 7 in RLE2, I'm required to encode it as a run of length 7. I don't get a choice. So although it's weird, it's not actually a feedback loop, which is sort of comforting. Oh, here's a question that I just answered. So I could go further, and if I really want to analyze this, I shouldn't really consider, oh, how many bits do I use to encode all the runs of length 9? No, because it's not as much as, I don't care as much about this number. What I care about is, okay, so I had a bunch of runs of 9 zeros in a row. Okay, and I turned this into, with RLE2, a bunch of RAs and RBs. And those got encoded into apparently together 8 bits. The question is, how many bits did I end up using for each of the original 0 indices? So what is the number of bits per symbol once I'm done RLE2? And I can compute that. I have all the information I need to do that. So I know how many bits go into all of the runs of length 9 together. I also know how many 0 indices that corresponds to. It's going to be 9 times the number of runs of length 9. So if I look at the ratio, it turns out that when I look at runs of length 9, they get encoded with 0.89 bits per 0 index. So if I have a run of 9 0 indices, then each one of these ends up represented in the equivalent of 0.89 bits apiece. If I look at a run of 1 0 index, well, that becomes a single occurrence of RA. RA is 2 bits, so I'm using 2 bits per occurrence, 2 bits per symbol. But you'll observe here that RLE2 is definitely pulling its weight, because if I just left this sequence of 0 indices in the stream, I didn't do RLE2, well, then the 0 indices would show up along with lots of other things. So there's my 1, there's a 5, there's a 6, whatever. I would have to give the 0 indices their own prefix code. I perform Huffman coding, and we expect, because zeros show up so often, that of course Huffman coding would assign 0 a relatively short encoding. What's the shortest encoding we could get? Well, in the absolute best case, it's 1 bit long. So we encode 0 with a length of, it ends up being length 1. That occurs only if 0 indices occur more than 50% of the time, which we can't guarantee will be the case. But in the best case, a 0 index gets length 1, so 1 bit per symbol if we have zeros. Whereas here, observe that I have 0.86 bits per symbol. So RLE2 is definitely pulling its weight. Sure, in this case, it's 2 bits per symbol, but it's a trade-off. But if I look at the really long runs, so that run of length 5600, well, to encode the value 5658 in RLE2 using RA and RB, I would need 36 bits. But those 36 bits correspond to 5600 zeros. And that means if I divide that out, 0.01 bits per symbol. That's amazing. And of course, I couldn't achieve that with prefix coding alone. If I look at the average, so you might look at this and say, but look, there are these two, if I look at runs of length 1 and 2, which are the most common runs, they are encoded in more than 1 bit per symbol. They're encoded in 2 bits per symbol. Yes, but if I look at the average, so if I look at all the different zeros across all the runs of zeros, and I average out the number of bits per symbol, index 0 ends up, as a result of RLE2, being represented in 0.99 bits per occurrence. So just marginally better than the absolute best that I could hope for in the very best case if I used prefix coding alone. And this isn't even a full block. This is a 750K input. If I made the block even larger, this number might go down further. So this is the real machinery behind the compression advantage of BZip. It is actually just the clever trick used in the RLE2 stage. The reason RLE2 is so successful is that we're using RLE2 as leverage on top of BWT and Move-to-Front. BWT and Move-to-Front together produce something that is so well optimized for run length encoding that with the right choice of run length encoding scheme followed by prefix coding, we can ratchet up the compression advantage. So that's BZip2. We've talked about BZip2. Hopefully this discussion of that anecdotal example was helpful, but there's one other question that could be lingering, which is, wait a minute, we've spent all semester talking about how the big three are GZip, LZMA, and BZip2. And BZip2 certainly sounds like fun, but wait a minute, what's this 2 all about? Whatever happened to BZip1? Well, okay, first, so there was such a thing. There was a predecessor to BZip2. It wasn't called BZip1 because, as you'd expect, back when it was being developed, there wasn't some understanding that there was going to be a version 2, just a version 1. So it was just called BZip, not BZip1. But I guess we'll call it BZip1 for contrast with BZip2. So I'll tell you a little bit about that. The original BZip program, which I will call BZip1, although actually the original BZip program only made it to version 0.21, I think, it used a very similar pipeline to BZip2. So RLE1 followed by the BWT, then Move-to-Front, then RLE2. However, the last stage wasn't prefix coding. It wasn't Huffman coding or prefix coding. It was a different entropy coding mechanism called arithmetic coding. Arithmetic coding in general, especially at the time, was found to be pretty slow. So arithmetic coding is generally much slower for both compression and decompression than prefix coding. Once you've done prefix coding, so if you have a long stream of symbols, and you design a prefix code, keep in mind that when you create the prefix code, the running time of the algorithm you use to make the prefix code is proportional to the number of symbols you have, not the length of your sequence. You generate a prefix code and you come up with an encoding for each symbol, and then you just have to run through from left to right, generating the bits for each symbol, looking up the symbol in a table and generating it. So hopefully you can understand how actually performing prefix coding once you have the prefix code is pretty fast. Arithmetic coding is slow. It turns out that that wasn't the reason that BZip switched to using prefix coding. So the reason we went from BZip to BZip2, and this is based on, well, it was clear from context, but the designer's actually gone on record to say this. Arithmetic coding was encumbered by patents, by software patents. And as a result, although it was a clever thing, it was an interesting and powerful entropy coding technique, especially at the time it was being explored a lot. Once it became clear that it was encumbered by patents, everybody fled. Everybody ran away from it because nobody wanted to be sued. And especially back then, it wasn't really clear how much of a patented algorithm you could implement, even in open source software, without being sued. And so commentary from the designer has suggested that the reason that BZip was redesigned, it was rebuilt in a new version to use prefix coding, was because arithmetic coding was patented and the designer didn't want to be sued, basically. Prefix coding techniques, including the Huffman coding algorithm, are not patented, so there wasn't a problem there. Now, switching over to prefix coding also had the benefit of improving the speed of compression, because as I said, prefix coding is pretty fast. And take my word for it, it turns out arithmetic coding is generally quite a bit slower. Now, the problem is arithmetic coding can generally achieve a better compression ratio. So by switching over, the compressor was faster, which may have helped it gain widespread adoption, but it wasn't as good at compression as it would have been with arithmetic coding. So the main reason for the switch was just because the arithmetic coding was patented, and as we've seen, patents are a pretty big impediment to progress being made in compression. LZW got abandoned for similar reasons, although it turns out the things that took the place of LZW I think were sort of better. So deflate rose to fame in the vacuum created by LZW suddenly being unusable due to patent issues. And so it's also true that when the scheme was redesigned, there were some tweaks made. So the new bitstream format for the prefix code-based BZip2 also included some other improvements. That's where I think that extra block-based CRC was added to allow better error recovery. A few other tweaks were made, and yet still, as we saw in this lecture, there were still a bunch of places where in BZip2 we're sort of throwing bits away. We're wasting bits, not very many, but some. We're wasting bits that we could have saved with some more careful accounting practices. And so in the 90s, we had to give up on this BZip1 idea because arithmetic coding was patented, and computers maybe were a bit too slow at the time for arithmetic coding to be very practical in general. But it's not the 1990s anymore, now it's 2023. As far as I can tell, the patent issues on arithmetic coding are no longer a problem, but even if they were, in this course I have a certain amount of leeway to talk about patented things anyway, because this is education. But also, computers are pretty fast now, so maybe it's time, unlike the designer of BZip and those people designing schemes in the 90s, maybe we really owe it to ourselves to talk about arithmetic coding in more detail. So maybe we ought to do that sometime soon.